Hi, my name is Sejal Welankar. I'm a junior majoring in computer science here at Washington State University. And today I'm going to talk about exploring the structure of cold hardiness data to refine existing models. Cold hardiness is basically the ability of a plant to survive cold temperatures. The current model used to predict cold hardiness is based on 23 cultivars or genotypes. Washington is home to over 70 varieties of grapes with data available for more than 30 varieties. Therefore, the questions arise. Is there correlation between the data of the same cultivar across different seasons, and is there any relation between different cultivars for the same season? These datasets are large, and therefore, before we can apply any analytics, we need to study the shape of data. Data has shape, and that shape has meaning. This is where topological data analysis comes in. The basic idea of TDA is to extract shape from data. Cold hardiness is basically the ability of a plant to survive cold temperatures. The current model used to predict cold hardiness is based on 23 cultivars or genotypes. Washington is home to over 70 varieties of grapes, with data available for more than 30 varieties. Therefore, the question arises, is there correlation between the data of the same cultivar across different seasons, and is there relation between different cultivars for the same season? These datasets are large, and before we can apply any analytics, we need to study the shape of data. Data has shape, and that shape has meaning. This is where topological data analysis comes in. The basic idea of TDA is to extract shape from data. Topological data analysis isn't a single technique. Rather, it's a collection of approaches with the common theme of extracting shape from data. The two main approaches here are the mapper algorithm and persistence homology. I focused more on persistence homology throughout my internship, but let's briefly touch upon the mapper algorithm. uh, what what you basically do in the mapper algorithm is take a point cloud, pick a filter function, divide up your point cloud into subspaces based on that. You then apply clustering algorithms on these subspaces to get a graph which holds the main structure of your data. An intuitive way to think about this is that you look at data through different lenses. Depending on your choice of the filter function, your view of data is going to change. At the end of the mapper algorithm, you get a graph, whereas in persistence homology, you get a set of barcodes. Each barcode corresponds to the lifespan of a certain network structure, may it be a connected component or a hole in your data. Here's a quick animation to see how persistence homology works. To understand the shape of the data, we need to evaluate the connected components. How do we do that? Well, you pick a distance d, and then you connect points which are within this d distance of each other to create a simplicial complex. We apply methods from homology, and a central hole is detected. Now, dependent upon your choice of d, the connected components are going to change. This is like changing the lens to look at data and getting different views. In persistence homology, you evaluate graphs for all such distances d. Let's look at how, depending upon your choice of D, the connected components are going to change. So as you go from small to big, the number of components, connected components change. In persistence homology, we record the connected components and holes that arise for all such distances D. We record them as persistence barcodes. The start and end of a barcode signify for how long a particular connected component or a particular hole lasted. The start of a barcode is basically the radius or the distance d at which the connected component was born, and the end of the barcode signifies the depth of that connected component. Persistence barcodes can also be represented as persistence diagrams. I've put up 4 examples of persistence diagrams for 4 different cultivars for the same season. As I said, birth values correspond to the distance at which a feature is seen, and death values correspond to the distance beyond which the feature disappears. The longer barcodes manifest as points which are further away from the diagonal. Now, this information can be used in multiple ways, and I explored different avenues. One application of persistence homology is to take stable values and use them as parameters for clustering. This will make the shape of the data more apparent. Here's an example. This is the data of 4 cultivars for one season. It looks really messy and we have a large number of data points and no apparent structure is visible. I generated persistence diagrams for this and found that the most stable range was from 3 to 3.5. Therefore, I decided to use 3 as my distance for clustering. Here are the results of running dbscan on the dataset with epsilon as 3. dbscan generates a diagram with 9 clusters. This makes it easier for us to inspect the connections. Points of interest here are when, during a small time frame, we have points separating into different clusters. These are potential sites where we can see branching. The results from the previous experiment were definitely promising, and I'm looking into trying more and more combinations, but there is more that we can do with persistence homology. The future scope of this work is to explore the use of persistence images. These are stable vector representations of persistence diagrams. They were designed to be fed into machine learning tools. I tried inspecting persistence images for the same data set before and saw that these diagrams were skewed due to noise. I would like to look into using a more stable tool to implement persistence images. Additionally, one scope of persistence homology is to be used to refine our inputs for the mapper algorithm. I think that there is a correlation between the appearance of a hole in persistence homology with the branching events in the mapper framework. This is something that I would very much like to look into. Additionally, Paola and I made a custom data visualization tool for Agate. This is for frost mitigation datasets and has a bunch of features in it. Let me know if you need more information on how to access it. I'd like to end this presentation by thanking everyone who helped make this internship a success. I'd like to thank Marcus as all the data I worked on was from his lab. I'd also like to thank all my supervisors and the organizers of this internship because I learned a lot and I'm extremely thankful to Agate for giving me the opportunity to participate in research. And I'm very excited to see what Agate has in store for the future. Thank you.